Chapter 6 focuses on the electronic structure of atoms. Now, the first thing that we need to do is make sure we can interconvert between wavelength, frequency, and the energy of a photon of light. So we begin with this question, what is the frequency of 589 nanometer light? Well, you need to know this relationship. Lambda nu equals c, the speed of light. So this is the relationship you need to know. Lambda represents wavelength, nu is frequency, c is the speed of light in a vacuum. So when we rearrange and solve this problem, we're looking for frequency. Frequency is equal to the speed of light divided by the wavelength. And when we plug this in, the speed of light, which will be given on the front page of the exam, is equal to 2.998 times 10 to the 8th meters per second. And then in the denominator, the wavelength is 589 nanometer light. Now, as always, you have to pay attention to the units. This is in meters, so this needs to be in meters. And the easiest way to approach this is to write 589, and instead of writing nanometers, nano means times 10 to the negative 9 meters. That's just a different way of saying nanometers. And when we do that, the units of meters cancels, and we end up in units of inverse seconds, which is the unit of frequency. So this calculates out to be 5.09 times 10 to the power of 14 inverse seconds, or hertz. We could say that that was in hertz. Now, I will point out to you that you need to know this equation that I put in a box, but the constants will be given to you. This will be given on the front page of the exam. C is equal to 2.998 times 10 to the 8th meters per second. And since you have this equation, if you know wavelength, you can calculate frequency, and if you know frequency, you can calculate wavelength. The next question says, what is the energy of one photon of light with the wavelength of 589 nanometers? So you need to know this relationship. You need to know that the energy of a photon of light is equal to h nu. The energy of a photon of light is equal to h nu. Now, one thing that we can do also, since from this equation, and we need to know this, since from this equation, lambda nu equals c, we can rearrange this and we can get nu is equal to c over lambda. The frequency is equal to the speed of light over the wavelength, and we can plug that into this equation. So therefore, we would have the energy of a photon of light is equal to hc over lambda. Now, where did this come from? It came from the relationship E equals h nu, and I plugged in for this frequency. This is the lowercase Greek letter nu, c over lambda, so hc over lambda. And now we just plug this in. Now, h is another constant that will be given. It's a very small number. We'll be given that h is equal to 6.626 times 10 to the negative 34 joule seconds. It's not joules per seconds, but joule times seconds, joule seconds. So we'll plug those values in. And when we plug those in, h in the numerator is 6.626 times 10 to the negative 34 joule seconds times the speed of light in a vacuum, which is given on the exam, 2.998 times 10 to the 8th meters per second, divided by, and then we will divide by the wavelength. And again, the wavelength is in nanometers, but it needs to be in meters so that all the units will cancel appropriately. So we will write 589, and instead of writing nano, nano means times 10 to the negative 9 meters. So as you look at the units, you'll see that seconds cancels inverse seconds, and meters cancels meters, and that leaves joules, which is a unit of energy. And the energy of this photon of light, the energy of one photon of light, is equal to, when we calculate that out, it's equal to 3.37 times 10 to the negative 19 joules. That's the energy of one photon of light that has a wavelength of 589 nanometers. So if you know the wavelength or the frequency or the energy, you can calculate any of the other two variables that you need to know. So the next question says, what is the energy of 500 nanometer light in units of kilojoules per mole? Now, this is the energy of a single photon. In fact, we can write this as joules per photon. This is the energy of one photon of light with the wavelength of 589 nanometers. So what is the energy in kilojoules per mole? Well, let's do this as dimensional analysis. I'm going to write down what I want to know. I want to know the number of kilojoules per mole. And the number of kilojoules per mole, and I'm going to start with the energy in joules per photon. It's equal to 3.37 times 10 to the negative 19 joules per photon. And the first thing that I'm going to do, I don't want it in joules per photon, I want it in joules per mole. So I'm going to put photons in the numerator and mole in the denominator. How do I go from photons to moles? We go from photons to moles using Avogadro's number. There are 6.022 times 10 to the 23rd photons in 1 mole of photons. There's 6.022 times 10 to the 23rd photons per mole of photons. So now it's in joules per mole. We want it in kilojoules per mole because that's the unit that is usually the most convenient in chemistry. So I'm going to put joules down here. We're going to convert to kilojoules. To convert from joules to kilojoules, remember that kilo means 10 to the power of 3. And remember to always put the exponential term, the 10 to the power of 3, with the base unit, the unprefixed unit. 1 kilojoule is equal to 10 to the power of 3 joules. You put it with this unit because kilojoule means 10 to the power of 3 joules. So the unit of joules cancels, and now I have it in kilojoules per mole, and this calculates out to be, in kilojoules per mole, 203 kilojoules per mole. Okay, that's the energy of 1 mole of light of 589 nanometers. Okay, we'll go to question number 2 on the next page then. Question number 2. Be sure that you know the relative order of the electromagnetic spectrum. This is something that I want you to know, and you will be tested on it. So this lists several regions of the electromagnetic spectrum. So let's start off with just a quick review of the electromagnetic spectrum. Now what I like to do is I like to think of this in terms from left to right in order of increasing wavelength, but in order of increasing frequency and energy from right to left. Remember that a wavelength is inversely proportional to frequency. As the frequency increases, the wavelength decreases. As the frequency decreases, wavelength increases. And also, wavelength is inversely proportional to energy. The shorter the wavelength, the greater the energy. So energy is increasing from right to left. Now, in order to memorize this, focus on energy. First of all, if you start roughly in the middle of the electromagnetic spectrum, you have visible light. And what are the colors of visible light? Well, the mnemonic is Roy G. Biv. So the question is Roy G. Biv in order of increasing energy or in order of increasing wavelength? And it's in order of increasing energy. So visible light is in order of increasing energy. Energy increases from left to right. So Roy G. Biv. So really, you might say that light should be remembered as Vib G. Ure. Violet light is the highest energy form of visible light, and red light is the lowest energy form. If violet light is the highest energy form of visible light, what is just higher than violet light? Well, ultraviolet is higher. And ultraviolet light, which will give you suntans and sunburns and ultimately skin cancer, what's higher in energy than ultraviolet light? X-rays. And too much exposure to X-rays can give you cancer. And what's higher in energy than X-rays? Gamma rays. So I'm going to write the Greek letter gamma. Gamma rays. Gamma rays are much higher in energy than X-rays. These are cosmic radiation from the sun. It also comes from radioactive atoms. What's lower in energy than red light? Infrared light. I think of the infrared light that's used to warm the food in cafeterias. We see red or orange light because some of the visible light is there, but really it's the infrared light that's keeping the food warm. So what's lower in energy than infrared? Microwaves. Microwaves, and I write the lowercase micro, the lowercase Greek letter mu, which stands for micro. And then what's the lowest energy form of electromagnetic radiation? Radio waves. Okay, so jotted that down, and this says consider these portions. So microwave radiation, I'm going to go ahead and circle that. There's microwaves. I'm going to circle X-rays right here. I'm going to circle green light and orange light. Now when I do that, this becomes trivial. So notice different ways that I could ask this. Actually, there are 6 ways that this question could be asked. We could ask this question in order of increasing wavelength or in order of decreasing wavelength. In order of increasing wavelength, if we go increasing wavelength, wavelength increases from left to right. So it would be X-rays have a lower wavelength than green light, which is lower than orange light, which is lower than microwaves. So microwaves are the lowest energy form that's listed, and so microwaves have the highest or have the longest wavelength. So we could ask in order of increasing wavelength or decreasing wavelength, which would be the opposite. We could ask in order of increasing frequency. Now frequency increases from right to left. Here's frequency increases. It's inversely proportional to wavelength. So in order of increasing frequency, the lowest frequency would be microwaves. Microwaves are lower in frequency than orange light, which is lower in frequency than green light, which is lower in frequency than X-rays. So it could be asked this way. Or it could be asked, place these in order of decreasing energy. So energy increases from right to left. Gamma rays are the highest energy form. Radio waves are the lowest energy form. So if this increases from right to left, then what we can do in this particular case, if it increases in this direction, is decreasing energy is from left to right. So X-rays are highest in energy. Now this, since it's decreasing, we're going to say this is greater than in energy. X-rays are greater in energy than green light, which is greater in energy than orange light, which is greater in energy than microwaves. Okay, well, we'll look at the next question. Now, the next question has been modified slightly from some of the questions that you may have in your lecture notes. I changed this. Originally in the lecture note it said, made a transition from n equals 3 to n equals 5. And I turned this around because I want to comment on the negative sign. Transition from the n equals 5 to the n equals 3. Now, here's the idea. For an electron and a hydrogen atom, we have the energy diagram where the ground state is the n equals 1 state. That's the energy of an electron in an n equals 1 state. And then up here we have an electron in the n equals 2 state. And there's a big quantum leap from 1 to 2. Then we have from n equals 3, there's a much smaller quantum leap. And then n equals 4 is smaller still. And then n equals 5 would be right here. So n equals 5 is right here. Now the electron starts out in the n equals 5 state. So to designate that electron, I'm going to draw an up arrow, a half-head up arrow. That represents an electron in the n equals 5 state of a hydrogen atom. And it's going to make a transition to the n equals 3. So it's going to fall down from 5 to 3. Now if it falls down from 5 to 3, it's losing energy. But energy doesn't just disappear. So if it falls from 5 to 3, where does that energy go? It comes off in the form of a photon of light. And so the first part of the question is, was energy emitted or absorbed? Energy is emitted. The electron falls down and energy is emitted. So in this particular case, the question is it's emitted. If the electron goes from n equals 5 to n equals 3, then energy is emitted. Next, what is the change in energy? Well, this will be an equation that's given to you on the exam. So on the exam, you'll be given this equation that E sub n is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n squared. So this equation is given. You do not need to memorize this equation. Okay. What does it represent? It allows you to calculate what the energy is of an electron if it's in one of these states. This is the energy of an electron in the nth state. So for example, if n is 1, the energy of an electron in the first state, I would put a 1 in here and calculate this out. The energy of an electron in the second state, I'd put a 2 in here and calculate it out. So what is the change in energy? Well, delta always means final minus initial. The change in energy is equal to E final minus E initial. Now I can plug this in here, and the change in energy is equal to a negative 2.18 times 10 to the negative 18 joules times 1 over n sub f squared. Now that's the final energy, minus a negative 2.18 times 10 to the negative 18 joules times 1 over n sub I squared. Okay, so that's the delta E. I can factor out the negative 2.18 and make this a little bit simpler. Negative 2.18 times 10 to the negative 18 joules times 1 over n sub f squared minus 1 over n sub I squared. So notice you won't be given this form of the equation, but it comes directly from this. It's just the delta E. And so we can plug the values that we have in this equation into it. It's going to be negative 2.18 times 10 to the negative 18 joules times 1 over, and what's the final state? Well, it's falling from the n equals 5 to the n equals 3. This is n sub f. N equals 5 is the n sub I. So it's going to be 1 over 3 squared minus 1 over 5 squared. Now, when we plug that into our calculators and calculate it, then the delta E calculates out to be negative 1.55 times 10 to the negative 19 joules. Now, remember, in some of your notes, you may have a different number here. You may say n equals 3 to n equals 5. I changed these so that you could see one of these with a negative delta E. If it's a negative delta E, what does it mean? Yeah, I didn't realize I was off screen. Let's pull up here. If it's a negative delta E, what does it mean? It means that the atom is losing energy. A negative delta E means that the atom is losing energy. Energy is being emitted. So what is the wavelength of light that was emitted or absorbed? Now, it's emitted. What wavelength of light was emitted? Well, the wavelength of light must correspond to exactly the energy of this photon up here. It's the difference in energy. We can express that this way, that delta E, that the energy of the photon must be equal to the absolute value of the delta E. Now, the delta E is the change in energy that the atom underwent. And when this atom fell from a high energy state down to a lower energy state, then what happened is that whenever it fell from a high energy state to a low energy state, it gave off energy, and the photon has exactly that amount of energy. So the delta E is negative because the atom is losing energy. The energy of the photon is the total magnitude, the absolute magnitude of that delta E. So the energy of the photon is equal to, the energy of the photon of light is equal to 1.55 times 10 to the negative 19 joules. So what we did, we changed the sign. Delta E has a negative sign because it's losing energy. The photon itself is just the absolute value of that sign. Okay, so how do I calculate the wavelength? Well, I use two relationships. And once again, I'm going to ask you to be sure you know these relationships. You need to know, first of all, lambda nu equals C. Next, you need to know that nu equals C over lambda. You need to know E equals h nu, that's the energy of a photon, and you need to know that E is equal to hc over lambda. Now, it's just the top two equations you have to know. The second equation is derived from the first, and the fourth equation is derived by substituting nu, C over lambda, in for nu in this equation. So you need to know and be able to work with those relationships. These formulas will not be given on the exam. Okay, so I know the energy of the photon. I want to know the wavelength. So let's go over here and continue to solve this. So the energy of the photon is equal to hc over lambda. It's a plug-and-chug equation, and my recommendation on a plug-and-chug equation is that you rearrange the variables before you plug the numbers in. So I'm going to rearrange to solve for wavelength. Wavelength is equal to hc over the energy of the photon. What I did, I multiplied both sides by wavelength, and I divided both sides by the energy of the photon, so that the wavelength is equal to h. H is given on the exam. H is 6.626 times 10 to the negative 34 joule seconds. C is the speed of light in a vacuum, 2.998 times 10 to the 8th meters per second. And the energy of the photon is 1.55. That's what we calculated when we did the delta E up here, 1.55 times 10 to the 19th joules. So look at the units of joules. Joules cancels, and seconds cancels. So we end up in units of meters, which is a unit of wavelength. And so the unit of meters calculates out to be 1.28 times 10 to the negative 6 meters. For visible light, we normally like to express wavelength in nanometers. So let's do that conversion. I can go from meters to nanometers. Nano means times 10 to the negative 9. So I'm going to put 10 to the negative 9 with the base unit, the unprefixed unit. Meters cancels, I end up in nanometers. And this calculates out in nanometers to be 1,280 nanometers. And this is emitted. It's given off because the electron is falling from a higher energy state to a lower energy state. And that's the answer to number 3. Question number 4 asks us to give the complete and the abbreviated ground state electron configurations for several elements. So here's how we'll do this. We'll use the periodic table to determine the electron configuration of an element. First, you need to know that this is the S block, this is the P block, this is the D block, this is the D block, and this is the F block. So the S block, the P block, the D block, and the F block. The S block starts with 1. This is 1s, so 1s, 2s, 3s, 4s. The P block starts with 2, 2p, 3p, 4p, 5p. The D block starts with 3, 3d, 4d, 5d, and the F block starts with 4, 4f, 5f. So 1s, 2p, 3d, 4f, 1, 2, 3, 4, the S, P, D, and F block. And we're going to proceed across horizontally, element by element, until we get to the element that we're interested in. So we're going to neon right here. And so to get the ground state electron configuration for neon, we're going to start up here where hydrogen is. We're going to put neon colon, and this is the S block, this is 1s, so hydrogen and helium are both in the S block, so this will be 1s2. That gets us across horizontally. Now we go to the second period, and this is 2s, 1, 2, 2s2, and then we proceed across, and this is the P block. The P block starts with 2. 2p, 1, 2, 3, 4, 5, 6. 2p, 6. That's the complete electron configuration. The abbreviated electron configuration of neon would be to go to the noble gas immediately before it. So we'd write neon. The noble gas before neon is helium. Helium represents the inner core of neon. So the 1s2, these are the inner core electrons. The 2s and 2 and 2p6, these are the valence electrons. Okay, so helium is the inner core, 1s2, and then starting after that, it's 2s2, 2p6. This is the abbreviated electron configuration for neon. Okay. Next, we go to chlorine. Chlorine is right under fluorine on the periodic table. Okay. And so we look at chlorine, and we're going to try to determine the ground state electron configuration for chlorine. Then here's what we have. We're going to, for the complete ground state electron configuration, we start up here where hydrogen is in the S block. This is 1s2, hydrogen and helium together, 1s2. So I'll put chlorine colon 1s2. That gets us across the first row. Then we're at the second row. This is 2s2. And then we keep going. This is in the P block. This is 2p, 1, 2, 3, 4, 5, 6, 2p6. And then we go across to 3s2, so 1s2s, 3s2. It's a superscript 2 because there's 2 elements here. 3s2. And then we'll go over here to the P block. This is 3p. How do I know this is 3p? Because the P block starts with 2. 2p, 3p, 1, 2, 3, 4, 5. 3p5. 3p5. That's the complete electron configuration. Now here are the valence electrons, and so all the other electrons are inner core. These are the inner core. And so as I look at those inner core electrons, which electrons, which noble gas has the inner core? Well, neon does. Neon is 1s2, 2s2, 2p6. And so the shorthand for chlorine is to start with the noble gas right before chlorine, which is neon. So I'll put chlorine, colon, and in brackets we put neon. And then we only write what comes after neon. Now the only thing you can put in brackets is a noble gas. So we start with what comes after neon. We're right here. This is 3s2 because 1, 2, 3. 3s2, 3p5. 3s2, 3p5. The advantage of the abbreviated electron configuration is that you're focusing on the valence electrons. Chlorine has 7 valence electrons. The old Roman numeral number 7 tells us how many valence electrons. Chlorine has 7. 2 plus 5 is 7. Okay, next we go to chromium. So chromium is an exception, and I want you to know the exception chromium. We would expect for chromium, and let's just write this over here to the side. For chromium, we would expect to see 1s2 well, without giving the full electron configurations, we would expect to see for chromium, if I focus on the electrons past argon, I'm going to write this over here. Chromium would be argon. It comes after argon. That's the noble gas before chromium. And we would expect 4s2, 3d, 1, 2, 3, 4. 4s2, 3d, 4. But that is not the electron configuration that we get. That's not the electron configuration that we get. So I'll put an X through this. And that's because of the half-filled subshell rule. On the energy diagram, here's chromium. We have 4s. There's one 4s. There's 5 3d orbitals. 1, 2, 3, 4, 5. And if I put these in, 4s2, 1, 2, 3d, 4, 1, 2, 3, 4. Now, the 3d4 over here is only a partially filled subshell. What we really would like to see here is a half-filled outermost subshell. So the half-filled outermost subshell that we would expect to see here, we can get if this electron hops up to the higher energy subshell. Now this is exactly half full. 3d would hold a total of 10 electrons. When it has 5, it's half full. 4s can hold 2 electrons. When it's holding 1, it's half filled. And so instead of this, what we actually have for chromium, now let's just do the complete electron configuration first for chromium. And remember, it's an exception. So we'll start with right here, chromium, colon, 1s2, 2s2, 2p6. So that gets us 1s2, 2s2, 2p6. Next, 3s2, and then we go across 3p6. And then 4s2 is what we would expect, but chromium is an exception. We get 4s1, 3d5. This is an exception. So you need to know chromium and copper, they are exceptions. They are the only exceptions I will ask. They are the only exceptions in the first 36 elements. The first 36 elements go through krypton. Of the first 36 elements, only chromium and copper are exceptions. The abbreviated electron configuration for chromium would be, I go to the noble gas just before chromium. Here's chromium, and so I go to the noble gas before it, which is argon. And we would expect 4s2, 3d4, but because of the half-filled subshell rule, we get 4s1, 3d5. Okay, and if you're using a different set of notes, you'll see a different element here, but we're going to omit that and just do iron right now. So look at iron. It's a transition metal, so let's just do the abbreviated electron configuration. The noble gas is argon, and following argon, this is not an exception, so 4s2. I know it's 4s because 1s, 2s, 3s, 4s2. And then 3d, 1, 2, 3, 4, 5, 6. 3d, 6. So that's the abbreviated electron configuration for a chromium atom. Okay, well, let's look at the next question then. The next question says, is nickel, so nickel is element 28. And it asks, is nickel paramagnetic or diamagnetic? So here's nickel. Well, I want you to know these terms, paramagnetic and diamagnetic. So let's jot those terms down to begin with. The term paramagnetic means it has unpaired electrons. Paramagnetic, it has unpaired electrons. Now, by unpaired electrons, that means that in some of the orbitals, it has electrons with upspin, but none pairing it up with downspin. Diamagnetic, in contrast, that describes an atom whose electrons are all paired. All electrons are paired if it's diamagnetic. So that if we have 3 different orbitals, if it's diamagnetic, 1, 2, 3, 4, 5, 6. Every one of those is paired up. There are no unpaired electrons, so this would be diamagnetic. So let's look at nickel. In order to answer this, don't just look at the periodic table. Do the electron configuration. So for nickel, I'm going to do the abbreviated electron configuration. The abbreviated electron configuration for nickel. The noble gas before nickel is argon. And so I'll put argon in brackets. And then immediately following argon, this is 4s2. And then we'll count up to nickel. 3D, this is 3D because the S block starts with 1, the P block starts with 2, the D block starts with 3. 3D, 1, 2, 3, 4, 5, 6. I stopped it down. Let's go 3D. 1, 2, 3, 4, 5, 6, 7, 8. 3D8. So that's the electron configuration. Now we've got to figure out how many electrons are paired. So let's draw an energy diagram. And when we draw the energy diagram over here, let's try that again. Let's draw this energy diagram. Then the 4s2 are lower in energy. So there's 2 electrons. And then the 3d are higher in energy. Now how many 3d orbitals are there? You need to know that there are 5 3d orbitals. Now one way to keep that in mind, in the D block right here, there's 10 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And since each orbital can hold 2 electrons, that means there are 5 different 3d orbitals. 1, 2, 3, 4, 5. So we're going to put those 8 in. Now we have to follow Hund's rule. Hund's rule says parallel before paired. Hund's rule says parallel before paired. Parallel before paired. So when I put those electrons in, 3d8 for nickel, I'm going to do a 1, 2, 3, 4, 5, 6, 7, 8. Now when you do it this way, this becomes an incredibly easy problem. There are 2 unpaired electrons, and so the answer is that nickel is paramagnetic with 2 unpaired electrons. The answer is nickel is paramagnetic and it has 2 unpaired electrons. It has 2 unpaired electrons. Okay, well, this was a question that was not in the original notes, but I've added this, and so be sure that you understand that. Now let's look at question number 6. We'll look at question number 6 at the top of the next page. And I've renumbered some of these questions because I've added to it. So as we look at this, place the following forms of electromagnetic radiation in order of increasing wavelength. So this is similar to the question that I showed you a little bit earlier. And once again, I'm going to jot down the electromagnetic spectrum. You need to know the relative regions of the electromagnetic spectrum. And on this spectrum, wavelength increases in this direction, whereas energy and frequency increase in this direction. And here's how I remember it. I start with visible light, but visible light's in order of increasing energy, so it's going to be Roy G Biv. Because violet light is higher in energy than red light. Energy increases in Roy G Biv is an order of increasing energy. Higher in energy than violet light is ultraviolet. You get sunburns and skin cancer. Higher in energy than ultraviolet is X-rays, and even a small exposure to X-rays can give you cancer. And the highest energy form are gamma rays, and if you were exposed to gamma rays, they would fry you. They're highest in energy. Lower in energy than red light is infrared light. That's used to warm food in cafeterias. Lower in energy than infrared are microwaves, and the lowest energy form are radio waves. Okay, so it helps me tremendously to just jot this down because you don't want to miss a problem like this. So it's all asking about the same one, so let's just circle each of these. Here's gamma rays. I'm going to circle these. Microwaves over here. We're going to have orange light. We're going to have green light. We're going to have ultraviolet light. Now this says in order of increasing wavelength. Well, wavelength increases from left to right. So increasing wavelength will be gamma rays first, and then X-rays. So gamma rays and then X-rays, so it can't be A. Can't be B because gamma rays has to be first. Gamma rays and then, I'm sorry, not X-rays, gamma rays and then ultraviolet. So C has gamma rays and then ultraviolet. D starts with microwave. Here, gamma rays and then microwaves. It's not this, so it's got to be C. Gamma rays, ultraviolet, green, orange, and then microwaves. So we got that in order. Okay. The next question number 7. If a photon has a frequency of 4.0 times 10 to the power of 15 hertz, its wavelength in nanometers is, well, here again we're going to use this equation. You need to know this equation, that lambda nu equals c, the speed of light. And I know the frequency. Nu is the frequency. I want to know its wavelength, so I'm going to rearrange this off for wavelengths. Wavelength is equal to c over the frequency. C is 2.998 times 10 to the 8th meters per second. The frequency is 4.50 times 10 to the 15th hertz. 4.50 times 10 to the 15. Now, I'm not going to write hertz. What is another way to say hertz? Another way to say hertz is to say seconds to the minus 1. That's hertz. So up here I have seconds to the minus 1, and here I have seconds to the minus 1. They cancel out. And that leaves it in units of meters, which is the appropriate unit for wavelength. When we calculate that, we get 7.5 times 10 to the negative 8. I wrote 4.50. This should be 4.0. 4.0 times 10 to the 15th. 7.5 times 10 to the negative 8 meters. Now let's convert that to nanometers because all these are in nanometers. I'm going to go from meters to nanometers. Nano means times 10 to the negative 9. It goes with the base unit, with the unit without the prefix. And so 10 to the negative 9 meters equals 1 nanometer because nano means times 10 to the negative 9. And this calculates out to be 75 nanometers. 75 nanometers. And so the correct answer is choice E. The next question, number 8, says, what is the complete ground state configuration of arsenic? Now, rather than look at each of these, let's just jot it down. I'm not even going to look at these. I'm going to cover this up. Here's arsenic, AS. So let's give the complete ground state electron configuration. Well, let's see. Let's raise it up so you can see it. Sorry about that. Okay, and for arsenic, here's arsenic right here. So we're going to I'm going to cover up these electron configuration, not even look at it. I'm going to start up here, 1s2. Arsenic is 1s2, and then we go across 2s2, and then 2p6, then 3s2, and then 3p6, and then we go across to 4s2. Now we're in the D block. The D block starts with 3. The S block starts with 1. The P block starts with 2. The D block starts with 3. 3D10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3D10. And then we're back to the P block. The P block starts with 2. 2P, 3P, 4P, 1, 2, 3. 4P3. 4P3. Now as I look at this, just glancing at this, I see a 3F3. There is no 3F orbital. I see 4d6. I can rule that out. There's no 4d6. So I'm ending with 4p3. So let's look at each of these. 1s2, 2s2, 2p6 is correct so far. 3s2, 3p6. Then it says 3d2, 4s10. So that's not correct. You can't have 10 electrons in a 4s orbital, so it's not A. I look at the next one. 1s2, 2s2, 2p6, 3s2, 3p6. 4s2. Now this says 4d10. It's not 4d10, it's 3d10. And so it can't be B. So it's got to be D. 1s2, 2s2, 2p6. That's what we have here. 3s2, 3p6. 4s2, 3d10. 4p3. And so D is the correct answer. Okay, the next question asks, what is the name of the orbital shown? So you need to know the shapes and names of the orbitals. Very quickly, here are the shapes of the orbitals. If this is the x-axis and the y-axis, if you have a perfectly spherical orbital, this is an s orbital, such as a 1s orbital or a 2s orbital. Now, that would be an electron cloud. And to symbolize this as electron cloud, I'm going to shade this in with a pencil. That's a 1s or 2s or 3s, etc. An S orbital is a spherical orbital. Next, we have a 2p orbital. If this is the x-axis, then the 2p sub x has a dumbbell shaped with 2 lobes on either side on the x-axis. And so I'll shade in this. If you have a 2p sub y, it's on the y-axis. 2 lobes, a dumbbell-shaped orbital. This is 2p sub y. And if I have a 2p sub z, it's on the z-axis, which comes in and out of the plane of the paper. So 2 lobes right there. This would be a 2p sub z. So you need to know the shapes of these orbitals. Next, you have 5 different 3D orbitals. So we have 3D XY, so that if you are in the XY plane, this is the x-axis and the y-axis, it's a 4-leaf clover where the lobes are located in the quadrant and not on the axes. So it's not on the axes, not on the x or y axes. It's in here, which is called the quadrant. It's in the quadrant, not on the axes. That's the 3D XY. The two others are very much like this. They just have a different perspective, the 3D XZ. To see this, I'm going to change my perspective. In this first one, I'm looking down the Z-axis. Now I'm going to look down the Y-axis. This is the X-axis and the Z-axis. And once again, this is a four-leaf clover type of shape. That's the 3D XZ. And the 3D YZ has a four-leaf clover, but it's perpendicular to both of these as well. So if this is the Y-axis and the Z-axis, we've changed our perspective. Then you get four lobes. So those are the four normal-looking 3D orbitals. Then you have two, this is 3D YZ. Then you have the two oddball orbitals. The two oddball orbitals are, first of all, the 3D x squared minus y squared. This, if this is the x-axis and the y-axis, this has four lobes, but they are located on the axes and not in the quadrant. And so this is the 3D x squared minus y squared. And then the fifth one, and I ran out of space, I have to draw it over here, is the 3D z squared orbital. So if this is the z-axis, and it doesn't matter if this is x or y because it's symmetric about it, this looks like a p orbital with a donut around its belly. Okay, so there's a, looks like a p orbital with a donut around its belly. As it turns out, that's what this is. So this is a dz squared orbital. The correct answer to number 9 is choice D. Number 10. According to the off-bow procedure, which orbital is it filled immediately after a 3D subshell is filled in a multi-electron atom? Now, you don't memorize this. You use the periodic table. This is how we get electron configurations. Off-bow means building up. Off-bow means building up. You're starting with the lowest energy orbitals and building up. And the periodic table is arranged in a way that it automatically does that. So as I look at this, first of all, let's find the 3D subshell. Well, this is the S block, the P block, the D block, the F block, so it's going to be in this block. Where's the 3D subshell? Well, the S block starts with 1 S. The P block starts with 2 P. The D block starts with 3D. So these 10 elements are in the 3D subshell. And as you fill them up, then the next orbital you come to when you're building up is right here. Now, it's in the P block. So which P block? Well, the P block starts with 2. This is 2P, 3P. This is 4P. And so the correct answer is choice A. It's 4P. Okay. Number 10. Number 10 says that microwave ovens operate by irradiating food with microwave radiation, assuming that the wavelength of this radiation is 15 centimeters. What is the energy of this radiation expressed in kilojoules per mole? So you need to know these relationships. You need to know that lambda nu equals C. You need to know that nu equals C over lambda. E equals h nu. This is the energy of a photon, and I can plug in for nu, C over lambda, so E equals hc over lambda. Now, when we, let me write lambda here this way. Whenever we do this, we are given the wavelength. We're given the wavelength, which is lambda. And we're asked for the energy. Now, and so I'm going to use this equation. Now, remember, I didn't write subscript photon, but this is really the energy of a photon, the energy of a single photon. Now, the question asks, what is the energy in kilojoules per mole? This is not a mole of photons. This is one photon. It's equal to hc over lambda. So h and c will be given on the exam. H is a constant, Planck's constant, 6.626 times 10 to the negative 34 joule seconds. C is the speed of light in a vacuum, 2.998 times 10 to the 8th meters per second. And lambda is the wavelength. Now, this wavelength is given in centimeters. Well, centi means 10 to the negative 2. So instead of writing centi, I'm going to write 10 to the negative 2. I'm going to put 15.0 times 10 to the negative 2 meters, because centi means times 10 to the negative 2. And the units of meters cancels, and the unit of seconds cancels. And that leaves it in units of joules, which is the unit of energy. So the energy of a single photon, when we have that, calculates out to be, let me do that, and I'm getting 1.32 times 10 to the negative 24, and this is joules per photon. But to get this in kilojoules per mole, so I want to know the number of kilojoules per mole, I'm going to take the energy per photon, 1.32 times 10 to the negative 24 joules per photon. I'm going to say times, draw a line. There are Avogadro's number, 6.022 times 10 to the 23rd photons per mole of photons, and I'm going to convert joules to kilojoules. And I put joules in the denominator, so it will cancel. Kilo means 10 to the power of 3, so I put 10 to the power of 3 with the unprefixed unit. So photons cancels, and joules cancels. This leaves me kilojoules per mole. And when we calculate that out, we get 7.98 times 10 to the negative 4 kilojoules per mole. 7.98 times 10 to the negative 4 kilojoules per mole, which is choice A. Okay. The next thing that we want to do is we want to be sure that we understand, let's pull it down just a little bit, be sure that we understand the three rules. So there are three rules you need to know. First of all, the Pauli exclusion principle. The Pauli exclusion principle. And it says you can have a maximum of 2 electrons as long as they have in an orbital, as long as they have opposite spin. A maximum of 2 electrons per orbital with opposite spin. Then we have the Aufbau procedure. Aufbau means building up. You start with the lowest energy orbital and build up. And then Hund's rule is parallel before paired. Hund's rule is parallel before paired. Now, this is drawn horizontally, which is how we often depict these. But if we think on the energy diagram this way, here's our energy diagram where we have 1s, 2s, and 2p. So here's the 1s orbital, a 2s orbital, and 3 different degenerate 2p orbitals. Remember, the word degenerate means they're equal in energy. And I have 1s2, so 1, 2. 2s, 1, and then 2p, 2. Well, this is incorrect. Because if you start at the bottom and build up, then when you get to 2s, you've got to put 2 electrons in it before you go to the next one. And therefore, this is incorrect. It's incorrect because it violates the Aufbau procedure. It is not building up. So C is the correct statement. This electron configuration violates the Aufbau procedure. Now, I mentioned earlier that you have to know that chromium and copper are exceptions when we determine the electron configurations. So this asks for the complete ground state electron configuration for chromium. So if I put the periodic table here so I can focus on chromium, I'm going to write it down first before I look at this. Remember, it's an exception. So for chromium, it's going to be chromium colon 1s2, hydrogen, helium, 2s2, 2p6. Now we come to the next period, 3s2, 3p6, 1, 2, 3, 4, 5, 6, 3p6. Now we expect 4s2, 3d4, but that because it wants a half-filled subshell, this will be 4s1, 3d5. Okay, so as I look at this, let's focus on these last two, see how many got these right. So this one says 4s2, 4d4, so that's wrong, so it can't be A. 4s2, 3d4, that forgot that this is an exception. 4s1, 4d5, it's not 4d5, it's 3d5, so that's wrong. It can't be C, A, B, or C. And D, this says 4s1, 3d5, so that fits. Just check E. This is 3p6 and then 3d6. It doesn't have the 4s1, it's got 3d6, so that's wrong. So only D is left. Let's check and see if this is correct. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5, and D is correct. So be sure that you know chromium and copper, because they are exceptions to the normal order of filling. Okay, we'll look at number 13. Now this asks us to compare the sizes of atoms and ions. Now first of all, this asks about magnesium and sodium. So we're going to look on the periodic table. By the way, when you see a question like this, we have Roman numerals. Don't look at A, B, C, and D. Look at each Roman numeral one at a time and determine which one is correct before you look down. So starting with the Roman numerals, is magnesium larger than sodium? Here's sodium and here's magnesium. And here's what you have to know. Now, first of all, these are neutral atoms. There's no charge. You need to know that for atomic size, atomic radii, it increases going down the periodic table, but it decreases going across. So it gets bigger going from right to left. That is, the atoms get bigger as you go down, but they get smaller as you go across. So magnesium is smaller than sodium. So 1 is false. Magnesium is smaller than sodium. Next, sodium plus 1 is larger than magnesium plus 2. Well, what we need to do here is we need to look at the electron configuration and the nuclear charge. So sodium plus 1, as we look at Roman numeral 2, sodium plus 1 has the electron configuration of 1s2, 2s2, 2p6. It's the same electron configuration as neon. It's lost an electron. It's the same as neon. Magnesium 2+, when it loses 2 electrons, it's also the electron configuration of neon, 1s2, 2s2, 2p6. They have the same electron configuration. What term do we use to describe that? We use the term isoelectronic. They have the same electron configuration. So how can I determine which is bigger? I have to look at and consider the nuclear charge. The nuclear charge is the number of protons. Sodium has 11 protons, a positive 11 in the nucleus. So the Z is plus 11. It's got 11 protons and 10 electrons. Magnesium has a nuclear charge of plus 12. So the rule that we learned, Z equals plus 12, the rule that we learned is when you are comparing isoelectronic ions, and these are isoelectronic, the same number of electrons, the same electron configuration, they get smaller with increasing nuclear charge, and that should make sense. I have more positively charged protons here pulling the electrons close to the nucleus. So magnesium, this is smaller than sodium, which is larger. They both have the same number of electrons, but magnesium has more protons pulling them in more tightly. By Coulomb's law, this is smaller. So this says sodium is larger than magnesium. That's a true statement. Next, magnesium 2+ is larger than oxide. So here's oxide, here's magnesium 2+, and here's oxide. Let's, for Roman numeral 3, let's just write the electron configuration for oxide, O2-. O2- has 2 more electrons than the neutral oxygen. It's the same as neon also. It's also isoelectronic. O2- is 1s2, 2s2, 2p6. This is isoelectronic as well. So what is the nuclear charge for oxide? Well, oxygen has 8 protons, so it's plus 8. So when I'm comparing magnesium and oxide, they have the same number of electrons, but magnesium has a lot more protons, 12, to pull them in very tightly than oxygen does. So magnesium is much smaller. So this is a false statement. Magnesium is not larger than oxide. Oxide is bigger than magnesium. They both have the same number of electrons, but oxygen does not have as many protons to pull them in together. Next, phosphorus is larger than oxygen. Well, here's phosphorus and here's oxygen. Now, atoms get bigger going down, they get smaller going across. Phosphorus is bigger than nitrogen, and nitrogen is bigger than oxygen, so phosphorus is bigger than oxygen, so that's a true statement. Roman numeral 4 is a true statement. So when we look at the answer, the correct answer will be choice C, Roman numerals 2 and 4. And you reason through that by looking at each one of these individually.